So, if I have a formula like this that has more than two elements, a formula has more than two elements, the first thing you should do is go to this common ions list and look through the common ions list and see if you can find some part of this formula that looks like one of these common ions. Okay? So you start searching through, comparing it to the formula that's up there. And you get right down here, if you're careful and look and do a good job, you're going to see there's an NO3 negative right here. Well, NO3 looks just like that, except it's got a negative charge on there, doesn't it? That makes sense? So, this is a charged particle and a charged particle. They're going to neutralize each other. This is a polyatomic ion. Look where it says polyatomic anions here, okay? That means that the formula is a formula for an ionic compound. If there's a polyatomic ion in there, this must be an ionic compound. So, one of two ways that you can tell if you have an ionic compound is if there's a polyatomic ion in the formula. If there's a polyatomic ion in the formula. That's a polyatomic ion. It's on the common ions list right down here. This must be an ionic formula. Okay? Here is another kind of formula that doesn't have a polyatomic ion in it. And it represents the other kind of compound, the other kind of formula that would be an ionic compound. In this class at least, okay? What we want to do is anytime you want to designate any formula that has a metal bonded to a nonmetal. Well, here's another reference in your test references for determining whether you have a metal or nonmetal. It's just a periodic table, and this stair step right here divides metals over here from nonmetals over here. So if I only have two elements, then I'm going to look on the periodic table and see if one of those elements is a metal and one of those elements is a nonmetal. There's magnesium and there's chlorine, a metal and a nonmetal. One on one side of the stair step, one on the other. This is another kind of ionic compound. So just looking at the formulas, you can tell that this is ionic because it's a polyatomic ion, and this is ionic because it has a metal bonded to a nonmetal. Okay? There are only two kinds of compounds that break up when you write a complete ionic equation. Two kinds of compounds that break up when you have an ionic equation. One of those kinds of compounds is both ionic and aqueous. One of those compounds is both ionic and aqueous. Both of these are ionic. Both of them we figured out were aqueous. Now, if you didn't know they were aqueous, if all you had was just the formula, how would you find out that that's an aqueous compound, assuming there's water around? You use the solubility rules. Okay? Andrew? Take a look at this formula. AgNO3. Okay? How am I going to tell that that's, if there's water around, how can I tell that's aqueous? The activity series is only used for determining if you have a driving force for a single replacement reaction. The question here is, if there's water around, will this compound be aqueous? How do you tell that? And how do I use the solubility rules? Tell me what to do with them. Here they are. Yeah, well, hold on. This is actually Andrew's question, okay? Just give me a second. You know how to use the solubility rules, Andrew?
Yeah.
Okay. Tell everybody in the class, how am I going to use these solubility rules to find out this is going to be aqueous if there's water around?
Look for the ionic compound and then you see if it like pairs with the other.
What did you say? Compares?
Pairs.
Pairs with the other one? Okay. Well, when you said ionic compound, this is an ionic compound, the whole thing. Do you mean just part of it? So what you mean is the ion, not the ionic compound. Okay? So you're looking for an ion in the formula, either the Ag or the NO3. See if it's on the solubility rules. And be careful to check for those exceptions to see if this is going to be aqueous. Okay? Lisa, what part of the solubility rules tells you this is an aqueous compound, if it does? Or it tells you that it's a solid? Well, which solubility rule? Read the solubility rule that applies to this. Do you have your test references? Where are your test references? You need test references every day. Okay, so all of these, including nitrates, are soluble. Soluble means that if and only if there's water around, it will be aqueous. Okay, you just can't assume it's going to be aqueous anytime it's there. You have to figure out if there's water around. So there's some things you have to figure out. If there's water around, it will be aqueous. Okay? If there's water around, Abdiel, tell me if this will be aqueous or not, and tell me how you know. You got your test references in front of you? Okay. Look in the, well, first of all, what do you name this part of this compound?
What do you name it?
What's the name of it? Don't say it, please. Let him answer.
I just thought about it.
Huh? And how do you know that if you didn't know just by looking at it? Where would you look for it? Where would you look for it? On the periodic table. What about this part of the compound? Don't whisper it, please. Okay, it would be chlorine, except that it is bonded to something else, and it's the last thing in the formula. So now what do we call it? Chloride. Look now in the solubility rules. Look in the solubility rules, Abdiel, and tell me if you see either silver or chloride listed. Did you say yes? Okay, where is that? Under all nitrates. So it says that all chlorides, bromides, and iodides. And this is in the soluble section, so that means chlorides, bromides, and iodides are almost all soluble unless they're bonded with silver, lead, or mercury 1. So is that bonded with silver, lead, or mercury 1?
Yeah.
So is it going to be soluble? It's going to be, if there's water around, is it going to be aqueous? It's going to be what? Solid. Okay? That's how you use the solubility rules. It's really pretty simple, but you have to practice with it to get good at it. All right. Wait a minute, that's not the right one. Here's the one back one right here. All right. Now, if you don't have this in your notes, make sure you write it down. There are only two kinds of formulas that break up when you write a complete ionic equation. There are only two kinds of formulas that break up when you write a complete ionic equation. The two kinds of formulas are, one, both aqueous and ionic, and the other kind is both aqueous and acid. They are, one, both aqueous and ionic, two types of compounds. Two types of compounds. Only two types of compounds break up when you write a complete ionic equation. And each type of compound has two requirements. Each type of compound has two requirements. Okay? It has to be both aqueous and ionic, or both aqueous and acidic. Yeah, only two kinds of compounds, 1, 2, break up when you go from writing a regular balanced equation to writing a complete ionic equation. Only two kinds of compounds break up when you write a complete ionic equation. And each of those kinds of compounds have two requirements. So it's not enough to be aqueous. It's got to be aqueous and ionic, or aqueous and acid. It's not enough to be an acid. It has to be acid and aqueous. It's not enough to be ionic. It's got to be ionic and aqueous. Does that make sense to everybody? Okay. So now then, let's look up here at this equation we're starting with. Look at the equation we're starting with here. If you don't have it written out, make sure you have it written out. And I want you to identify in some fashion on your paper, in writing, which of these compounds meet 1 or 2 here. Which of these compounds are we going to break up when we write the ionic equation? Which compounds are going to break up when we write the ionic equation? We have to first break up the complete ionic equation, and then we'll have to get to the net ionic equation after that.
Oh, are you talking about the two things that make up the compound of aqueous and ionic? When you say both aqueous and ionic, what's the both? What's the thing?
Well, if it can be ionic and be something else besides aqueous, and it wouldn't break up.
So basically, you saying if they got an aqueous inside, they meet one of the requirements.
Yes.
If the compound is ionic, then that's when you.
If it's both aqueous and ionic, then it meets both requirements. If it's both aqueous and acidic, it meets both requirements. No, I just want you to somehow identify in this equation which of these are going to break up. Okay? Identify which of these are going to break up.
So if they don't have the aqueous inside, one of that.
That's right. You got it. Okay, Ben, what about this formula over here? Is this one going to break up when we write the complete ionic equation?
Yes.
Why?
Because it's aqueous and it's aqueous and ionic.
How do you know it's ionic? It sounds like a question, not a statement.
Because
But Abdiel can tell you now.
Because on the common ion was the
NO3, the nitrate.
Yeah.
Okay, so there is a polyatomic ion in the formula. This must be an ionic compound. There's two kinds. The kind that has an ionic compound, the kind that has a polyatomic ion, and the kind that is made of metal bonded with nonmetal.